Hello and welcome. Today we're going to be discussing the problem make all distinct. In this question, we are given n integers between 1 and n and a fixed value k. And our goal in this problem is to determine the minimum number of times that I have to add k to each number so that all integers are distinct at the end of the process. So let's walk through an example together. Suppose that k is 2 and the array is 3, 3, 5, 6, 6. At the moment, we can see that there are two threes and two sixes. So these would be examples of non-unique elements. So those have to be corrected. So to correct the 3, what I can do is I can add k to one of them, turning one of them into a 5 because 3 plus 2 produces 5. But now I have a new problem. I now have two 5s. So what I have to do is I have to add 2 to one of the 5s to get 7. So now the first three values are all distinct. However, I still have the problem of two 6s. I can apply the sort of same idea where I'm going to add 2 to one of the 6s to produce 8. And now you can see that every single element is unique. So how many operations did I use to make A unique? I used 3 operations. And you can confirm for yourself that this is the minimum number of times that we need to apply the operation. So when you're thinking about solving this problem, you want to think of it as an operation minimization problem. And these problems are typically solved using a greedy algorithm. And here there's actually a very straightforward greedy idea. And the greedy idea is that if two elements are equal, I have to add k to one of them. That is the only option I have in this problem for resolving a pair of elements that have the same value. So I'm just going to repeat this over and over until all of the elements are distinct. If I do this, however, I'm going to run into a small problem, and the small problem is that the number of operations that I might have to apply can be on the order of n squared, which is problematic if n is 100,000. So if I have to apply 100,000 squared operations, I'm going to get a TLE error. To fix this, we can't apply the operations one by one. Instead, we have to come up with some solution that allows us to process the operations and count the number of operations in batches. And so what we want to do, the key observation in this problem is that we want to solve this question using a frequency array. Anytime a problem is going to ask about the number of numbers or having unique numbers or the presence of unique numbers or non-unique numbers, I'm always going to want to think of a frequency array. Why is a frequency array helpful for these problems? Well, if a frequency is 0, the element doesn't exist. If a frequency is 1, then the element is unique. And if the frequency is anything other than 1 or 0, then the element is non-unique, right? It occurs multiple times. So the frequency array stores exactly the information that I care about in this problem. So with this observation that we want to use a frequency array, let's try a slightly harder example. So let's try the example k equals 2 and a is equal to 3, 3, 3, 3, and so 5 threes in total. Why is this a harder example? Well, all of the elements are the same, so I'm going to have to apply a lot of operations in order to make them all unique. And what I'm going to do is I'm going to start with the frequency array representing this array A. So the way a frequency array works is each element stores the frequency of that index. So there are 0 1s, there are 0 2s, there are 5 3s, 0 4s, 0 5s, and so on. And what I can see here is that I've got 5 copies of 3, which means in order to get a unique copy of 3, I have to increase 4 of them by k. And when I do that, I'm going to end up with 1 copy of 3 and 4 copies of 5. So I can apply 4 operations in one batch, right? So I'm now left with 1 copy of 3 and 4 copies of 5. The key observation is that I didn't have to update the frequency array one step at a time in order to achieve this result. I can simply subtract this index by the amount that I have above 1 and then add it to the next index. So if this was index I would increase index I plus k by 4. And now when I'm looking at index I plus k, in other words 5, I can see that I'm left with too many copies of 5. I have 4 copies of 5. I can only have 1 copy of each number. So therefore, I'm going to have to move 3 copies of 5, and the only way I can move elements in this problem is by adding k. So I'm going to add k to 3 of these copies of 5 in order to achieve 3 copies of the number 7. So now I have 1 copy of 3, 1 copy of 5, 3 copies of 7. And I'm going to repeat this until eventually every element is unique. So I have 1 copy of 3, 1 copy of 5, 1 copy of 7, 1 copy of 9, and 1 copy of 11. And we're skip counting by 2s here because k is 2. If k was different, then we'd be increasing by different amounts. And what you can see is the number of elements we moved on each step is the number of operations we used on each step. So on the first step, we used 4 operations, then 3, then 2, then 1, for a total of 10 operations. So by solving this on a frequency array, we're able to batch the operations together. And the key idea is that if the frequency of any element is greater than 1, I simply have to move frequency of I minus 1 elements, all but one of the elements, to position I plus k. And I'm going to do that until I reach the end of the frequency array. So with this in mind, let's jump into the code. And then when we get towards the end of the code, we're going to talk about one more aspect of the problem that we're currently missing in this analysis. So going over to the left side of the screen here, we've so far just read in the input. Again, we have t test cases per test case, so I've created a solution function. Here is where we're going to be solving the problem. So we've got our value n and k, and this is our array of numbers. And this is the array that we want to make all distinct. So the very first step that we want to do is we want to calculate the frequency array. So we've created a frequency array here. This creates an array of size n, and we're looping over each element in the array A, and we're increasing that position by 1. So for each copy of the element AI, its slot in the frequency array increases by 1. So at the end of this loop, the frequency array will store the frequency of every number in A. Note that I'm subtracting 1 from all of the elements so that they fit well into my frequency array of size n. So I'm just 0 indexing the input. Then step 2 is a necessary step, but one that's easy to miss. In this problem, k can be negative, and in the situation where k is negative, instead of processing the frequency array from left to right, the key idea is that you'd want to process the frequency array from right to left. In my solution, I'm a bit lazy and I don't want to write out 2 different blocks of code. So what I do instead is anytime k is negative, I simply multiply k by -1 to make it positive, and then I reverse the frequency array. And by doing so, I can basically reduce the problem to the k is always positive case and save myself a little bit of extra work. However, if you don't like this trick, you can always just separate it out into 2 subcases. One case where you solve the problem going from left to right, and a second subcase where you solve the problem going from right to left. So feel free to solve the problem using either approach. And then the last step is the key aspect here. So we're going to loop over the frequency array from right to left, and we're going to push all the non-unique elements to the right. So anytime we see a non-unique element, we are going to push the amount of copies necessary to make it unique to the right. So if we have 5 copies of a number, that's too many. So we're going to push 4 copies to the right and leave 1 copy behind. If we have 4 copies of a number, we're going to push 3 copies of the number to the right and leave 1 behind. So we're pushing just enough copies of the number to the right in order to make the current element unique. So in order to do that, we're going to have our final count here, and we are going to create the variable move as frequency of I minus 1. And we only need to do anything if this value is positive, right? So this is how many we have to move on each step. It is possible that this is 0 or -1. If it's 0 or -1, we don't have to do anything and we can just skip to the next number. But if it's positive, then we are going to move those elements. So we're going to increase our operation count by the number of elements we're moving. And then the easy case is that the frequency at I plus k exists in the sense that this is a valid element in our frequency array. So namely, I plus k has to be shorter than the length of the frequency array, which is n. So if I plus k is shorter than n, then we can increase the frequency array at position I plus k by the number of elements we're moving. However, it is not guaranteed that I plus k is indeed less than n. And we have to handle the case where the frequency array of I plus k doesn't exist. One solution is that you can make your frequency array larger. However, you might run into some trouble if you try to make the frequency array large enough to store all possible values of frequency of I plus k. Um, in the worst case, I believe the size of the frequency array you'd need would be n times k, which is going to be on the order of n squared in some test cases. So you'd need too large of a frequency array. So if you just make your frequency array arbitrarily large, you're going to end up with a frequency array that is too large. So what I've done here is I've limited the frequency array to be size n, and then I'm going to create a second case that handles what to do if the numbers are going out of bounds. Going back to the right side of the screen, we're going to try to solve this test case again, but with a smaller frequency array. And the key idea is that since A has length 5, I want to fix my frequency array so that it also has length 5. So what we're going to see here is that the frequency array starts off very similar. I have 0 copies of 1, 0 copies of 2, 5 copies of 3, 0 copies of 4, and 0 copies of 5. Since I have 5 copies of 3, I have to move 4 of them away, and I'm going to be left with 1 copy of 3 and 4 copies of 5, just like before. And since I have these 4 copies of 5, I have to move 3 of them away, and I'm left with 1 copy of 5. However, when I do this, we'll see that these 3 elements are now out of bounds. They don't exist inside the frequency array, so I can't just update the frequency array by the amount that I'm moving. However, since it's out of bounds, I also know that there are no other elements that are stored here. There aren't any extra elements coming from other elements in the array A that could possibly be here. This is all the elements that are going to ever be in this slot. So what that means is I can just process all of these elements immediately using a math formula. And in particular, you're going to see that if I have 3 elements right here, one element will have to move 0 extra slots. In other words, one element can stay right where it is. One element will have to move 2 extra slots, or sorry, 1 extra slot. And then finally, one element will have to move 2 extra slots. So one element stays where it is, one element moves 1 extra slot, one element moves 2 extra slots. So you can see that if I have 3 elements, the number of extra moves that I'm going to have to expend to sort of satisfy these elements or make them unique is simply the sum of 0, 1, and 2. And in general, if I have, let's say, n elements that are out of bounds, I'm going to incur a cost of 0 plus 1 plus 2 plus 3 all the way up to n minus 1 extra moves to satisfy those numbers that went out of bounds. This is better known as simply n choose 2. So the final case here is that if the frequency array at I plus k does not exist, we're going to increase the count by move times move minus 1 over 2. This is just move choose 2. Again, if this is not obvious to you, you could use a for loop instead. However, this is one place where having a nice, strong competition math background can be helpful in a USACO exam. So counting arguments like this feel a little bit more natural. Thank you so much for watching the video, and have a wonderful rest of your day.